At first, there was a dense mass of matter. This mass underwent a massive explosion, which led to the creation of particles, atoms, stars, and galaxies that we observe today. For many years, this explanation was widely accepted by physicists. However, more recent research has introduced a new perspective, suggesting that the universe may not have had a definitive beginning as initially believed. Instead, it could be part of an ongoing cycle, where the universe goes through alternating phases of expansion and contraction, potentially in an infinite loop. Brian Cox, a renowned physicist, expresses skepticism about the theory of the Big Bang, arguing that something cannot emerge from nothing. This criticism adds an intriguing dimension to the discussion. Additionally, data from the James Webb Telescope has revealed findings that challenge the idea that the Big Bang marked the absolute beginning of the universe. This raises a fundamental question. If the Big Bang wasn't the start of the universe, then what was? Join us as we explore the origins of the universe, delving into the mysteries of the Big Bang and seeking answers to these profound questions. If you're interested in staying updated with the latest news about the universe and its surroundings, be sure to subscribe to our channel, like the video, share it to reach more people, and activate the notification bell. Scientists have developed a detailed understanding of the universe's early stages, known as the Big Bang theory. According to this model, the universe was once much smaller, hotter, and denser than it is today, approximately 13.8 billion years ago. During this time, all the components that make up our reality were created in a fraction of a second. In this theory, the universe, including stars and galaxies, was once as small as a peach and had an incredibly high temperature of over a quadrillion degrees. Remarkably, this story aligns consistently with all current observations. Cosmologists have studied everything from the afterglow electromagnetic radiation of the early universe to the abundance of lightest elements, and all the findings match the predictions of the Big Bang theory. Despite its apparent robustness, we know that this explanation doesn't offer a complete picture. There's still a missing piece to the puzzle: our understanding of the universe's earliest moments. This challenge arises largely from the limitations of our current theories. The combination of general relativity and high-energy particle physics provides a useful framework, but as we probe deeper into the universe's beginning, the mathematical complexity increases significantly, reaching a point where our existing methods are no longer adequate. One indicator of this difficulty is the presence of a singularity, a point of infinite density, at the beginning of the Big Bang. This concept suggests that the universe was once compressed into an incredibly small, dense state, which seems paradoxical. To solve this challenge, we need to explore new frontiers in physics and develop a theory that can address these limitations, offering a more complete understanding of the universe's origins. Our current tools and theoretical structures are not powerful enough to tackle this problem, so we need to create new physics that can encompass and explain gravity and the other fundamental forces at extremely high energies. This is where string theory comes into play. String theory aims to provide a physical model capable of unifying gravity with the other fundamental forces, especially at ultra-high energies. According to string theory, it could offer an explanation for the earliest moments of the universe. One of the concepts emerging from string theory is that of an aeon, derived from the Greek word meaning design or generation. This idea proposes that the Big Bang, as we understand it, might have been the result of a prior event, suggesting that it wasn't the absolute beginning but rather part of an ongoing cycle. The concept of a cyclic universe has led to the development of a related theory called cyclic cosmology. Although the idea of a cyclic universe has been considered for centuries, string theory provides a solid mathematical foundation for this concept. In cyclic cosmology, the universe behaves as though it endlessly oscillates between big bangs and collapses, in an infinite cycle stretching both into the past and the future. This theory was proposed by the prominent physicist Roger Penrose, who was awarded the Nobel Prize for his contributions. Penrose became fascinated by an extraordinary mathematical relationship between the early universe, characterized by extreme density, heat, and smallness, and the future state of the universe, which is predicted to be incredibly cold, expanded, and devoid of matter. The theory suggests that these two states could eventually become mathematically indistinguishable when pushed to their limits. Although it might seem impossible, the total absence of matter might be the driving force behind the creation of all the matter we observe today. From this perspective, The Big Bang could have originated from a state that was almost indistinguishable from nothingness, even though this nothingness still constituted a physical universe, just an empty one. The key lies in how this same state can be interpreted as both a cold, void universe and a dense, hot universe, depending on the perspective. The secret to this understanding lies in a complex mathematical process called a conformal transformation. This mathematical operation changes the scale of an object while maintaining its shape. Penrose demonstrated that the cold, empty state and the hot, dense state could be connected through this scale transformation, adjusting their spatiotemporal structures despite their differences in size. Penrose argues that, under these extreme conditions, the concept of time loses its relevance. In cyclic cosmology, the sequence of events moves from an ancient cold state to a young hot state. The hot, dense state arises as a consequence of the previous cold, empty state. However, this causal relationship doesn't follow the usual trajectory of time, as time itself loses its usual meaning in these extreme conditions. The cold, empty state and the hot, dense state exist on different timescales, meaning that from the perspective of an observer within its own time frame, the cold, empty universe would appear to be entirely separate from the hot, dense one. This radical view challenges our conventional understanding of the universe's origins and time itself, opening the door to new possibilities for the universe's past and future. The rise of life in the universe may alleviate the need for a finely tuned cosmos, making the vastness of the universe an intriguing concept. One fascinating idea that challenges conventional thoughts on the origins of the cosmos is that of timeless expansion, proposed within the framework of inflationary cosmology. Timeless expansion suggests that the universe undergoes an endless series of inflationary stages, each creating new regions of spacetime with potentially distinct physical laws. In this view, our observable universe is just one of countless regions within an eternally expanding cosmic foam. This concept of eternal inflation raises important questions about the nature of time and causality in a multiverse. If inflationary bubbles can continuously spawn new universes, the notion of a single, definitive origin becomes increasingly difficult to maintain. Instead, the universe appears as a dynamic, ever-evolving entity, embedded within a larger cosmic fabric of inflationary development. Recent advances in theoretical physics have sparked interest in alternative cosmological models that challenge the traditional narrative of a singular cosmic beginning. For instance, some theorists have explored the possibility of a cyclic universe, where the Big Bang is not a one-time event but part of an ongoing cycle of expansion and contraction. According to cyclic cosmology, the universe undergoes repeated cycles of creation, evolution, and destruction, each culminating in a cosmic collapse, followed by a new Big Bang. This model draws inspiration from both ancient cosmological ideas and modern theoretical frameworks, such as string theory. String theory, which proposes that fundamental particles are not point-like objects but rather tiny, vibrating strings of energy, naturally leads to the idea of a cyclic universe. It suggests that the universe could exist within a higher-dimensional spacetime, where cycles of expansion and contraction are the result of interactions between fundamental forces. While the cyclic universe hypothesis remains speculative and faces significant challenges regarding observational evidence and theoretical consistency, it represents a bold attempt to reconcile quantum mechanics with general relativity on cosmological scales. By proposing a consistent cycle of cosmic rebirth, cyclic cosmology offers a compelling vision of a universe without a definitive beginning or end, where each cycle builds upon the remnants of the previous one. In addition to theoretical models, observational cosmology has provided crucial insights into the early universe and its development over cosmic time. The discovery of the cosmic microwave background (CMB) radiation in the 20th century provided definitive proof of the Big Bang theory, offering a snapshot of the universe just 380,000 years after its inception. Detailed measurements of the CMB by satellites like Planck have enabled scientists to map temperature and density variations across the early universe with remarkable precision. Furthermore, observational cosmology has revealed the large-scale structure of the universe, uncovering the intricate web of galaxies, clusters, and cosmic filaments that span billions of light-years. By studying the distribution of galaxies and measuring their redshifts, cosmologists have been able to trace the expansion history of the universe and infer its age, composition, and ultimate fate. One of the most remarkable discoveries in observational cosmology is the existence of dark energy, a mysterious form of energy that permeates the universe and is driving its accelerated expansion. First inferred from supernova observations in the late 1990s, dark energy constitutes approximately 68% of the total energy density of the universe, making it the dominant component of the cosmic energy budget. The discovery of dark energy presents a major challenge to our current understanding of fundamental physics, as its origin and nature remain poorly understood. Several theories suggest that dark energy might be a manifestation of the vacuum energy predicted by quantum field theory, while others propose modifications to Einstein's theory of general relativity to account for the observed acceleration of the universe. In parallel with these observational endeavors, experimental physicists are actively searching for new particles and interactions that could provide clues about the fundamental nature of dark energy. Major projects such as the Large Hadron Collider (LHC) aim to push the boundaries of particle physics by colliding protons at unprecedented energies, potentially revealing new physics beyond the Standard Model. Advancements in astrophysical instrumentation have also allowed scientists to explore the universe across a broad spectrum of electromagnetic wavelengths, from radio waves to gamma rays. Observatories like the Atacama Large Millimeter/Submillimeter Array, ALMA, and the Hubble Space Telescope have revolutionized our understanding of star formation, galaxy evolution, and the cosmic distribution of dark matter. Looking ahead, next-generation observational facilities such as the James Webb Space Telescope, JWST, and the Square Kilometre Array, SKA, promise to provide new insights into the early universe and its fundamental constituents. These cutting-edge instruments will enable scientists to study the first galaxies, probe the epoch of reionization, and search for signs of primordial gravitational waves left over from the Big Bang. In conclusion, the quest to understand the origins of the universe represents one of the greatest intellectual challenges of our time. From ancient myths and philosophical inquiries to modern scientific theories and observational discoveries, humanity's exploration of cosmic origins has yielded profound insights into the nature of reality itself. As we continue to push the boundaries of knowledge and exploration, new theoretical models, observational techniques, and experimental breakthroughs are bound to shed light on the fundamental mysteries of existence and our place in the cosmos. The concept of endless cycles of the universe intertwines with physical science and reasoning, offering detailed explanations for their origins. However, despite the fascinating insights provided by Penrose's theory of cyclic cosmology, a deeper philosophical question remains. How did these cycles come into existence in the first place? This leads to a fundamental inquiry about the nature of physical reality itself. Why is there something rather than nothing? For our purposes, we will focus on physical explanations, exploring three possible scenarios regarding the origins of these cycles. First, there may be no intrinsic reason for their existence at all. Second, there could be an infinite series of cycles, where each new cycle represents a different universe, and the initial quantum conditions of each universe are somehow influenced by the remnants of the previous one. Finally, there is the possibility of a single cycle in a repeating universe, where the beginning of the cycle is explained by some aspect of its own end. These possibilities are compelling because they avoid the need for uncaused events and offer a more intricate explanation within the framework of physics. Penrose proposes the idea of an endless sequence of cycles, informed by his understanding of quantum mechanics. According to quantum theory, a physical system can exist in multiple states simultaneously until it is observed, at which point it randomly collapses into one state. Penrose suggests that each cycle is influenced by random quantum events that give rise to variations between cycles. This idea opens up exciting opportunities for experimental physicists, as it presents the potential to detect subtle traces or anomalies in the afterglow of the Big Bang. The quest to understand the origins and nature of the universe has been a fundamental pursuit for both humanity and scientific inquiry for centuries. From ancient philosophical theories to modern cosmological models, mankind has continuously sought to uncover the mysteries of existence. In contemporary astronomy and cosmology, the study of the universe's origins has led to groundbreaking discoveries and fascinating theoretical frameworks that challenge our fundamental understanding of time, space, and matter. One enduring question that has captivated physicists and cosmologists is the nature of the universe before the Big Bang. While the Big Bang theory has provided a compelling explanation for the universe's expansion from a hot, dense state to its current vast form, it leaves open the question of what, if anything, existed before this cosmic event. The idea of a pre-Big Bang state raises significant philosophical and scientific implications, pushing the boundaries of our understanding and inviting various theoretical models to address this question. One such proposal is the idea of the multiverse, which posits the existence of a vast collection of universes, each with its own unique physical properties and fundamental constants. Within the multiverse framework, our universe is merely one of many, each emerging from different initial conditions and governed by its own set of physical laws. The multiverse concept arises naturally from certain interpretations of quantum mechanics and cosmological inflation theory. According to inflationary cosmology, the rapid expansion of spacetime in the early universe could have led to the formation of pocket universes within a larger multiversal landscape. Each pocket universe would have distinct properties shaped by random quantum fluctuations during the inflationary epoch. While the multiverse theory remains speculative and difficult to test observationally, it provides an intriguing solution to the fine-tuning problem in cosmology. This problem refers to the apparent improbability that the fundamental constants of nature are precisely tuned to allow the existence of complex structures such as galaxies, stars, and life itself. In a multiverse scenario, the vast diversity of universes ensures that some will inevitably have conditions suitable for the emergence of such structures.